We'll be starting shortly. Everyone's here. In the same system has been going on this semester of having Turing Fellows from the University of Bristol speak at the Data Science Seminar Series. And this week, we're very fortunate to have Sid Jaggi. And I looked up his bio, and despite the fact that you've spoken before, I had not spotted that you've been to Caltech and MIT, so that's very exciting. Sid joined us from Hong Kong in 2020, and so spent the first year of working at Bristol not being with any physical meetings at all. So it's sad in a sense that we've asked you to give this talk online rather than in person, but I know that you speak very well, and so I'm very excited to have you speak. Today it's about the mathematics of deception, and I'll let you take it away after I just remind everybody about the code of conduct for JGI, which I'll just paste into the chat for anyone that's appeared since that was last posted. Okay, please take it away.
Thank you for the invitation. It's a pleasure, and thanks for the pressure, Dan, of apparently speaking well. So I'll be, as the title says, I'll be talking about the mathematics of deception. And since I was told that the audience would be perhaps a bit more general than just math or engineering or whatever, so I've tried to keep it at a relatively high level of exposition, relatively few proofs, mostly just hand-wavy intuition, a couple of proofs here and there, but mostly just high level. I'm happy to scribble if people have questions. I'll be keeping an eye on the chat window if people do have questions. So we can dive in at any point. And I'll try, of course, to leave 10 minutes or so at the end for questions, if any. Yeah. So let's dive into it. So at a very broad, high level of abstraction, as an information theorist, what do I deal with? What do information theorists deal with? So there's some information that comes into some system. It could be generated by some source. It could be generated randomly. There could be more structure to it. Then it gets processed somehow. Like maybe a sensor is looking at it. Maybe a transmitter is adding redundancy for the purposes of communication. Maybe it's being stored in a data server system or something like that. And at some point, noise gets added to the system. And then eventually you want to figure out something about that information. So you analyze it. If it's a communication system, you use a receiver, you try to figure out what happened, try to retrieve your data, right? So just at a very high level of abstraction, right? And and in particular, I'll often just use Alice and Bob as shorthand for these two entities over here, right? And at a very high level, well, not always, but for many of these information processing systems, if the noise is random, then Shannon theory has given us with some very good tools on figuring out what the fundamental limits are, how best to communicate, how best to store, to estimate, and so on. And we have schemes that meet these. In many cases, not all. In many cases, these schemes are even computationally efficient, and so on. So the emphasis of the talk today will be in a different direction. It'll be, well, what happens if this noise is adversarial? So sometimes I'll call him James the Jammer. Sometimes it'll be Calvin, because A, B, C, Alice, Bob, and Calvin. But whatever. And it turns out here, less is known. So I'll try to sketch again at a high level what is known, what's not. And in particular, I'll focus on certain types of things that the adversary can do, which random noise would rarely do, and therefore the impact that this has on the information processing task. All right. So, and yeah, so in particular, like you could think of it as sort of a SWOT analysis. What are the strengths and weaknesses of each of the parties? So on one hand, there's Alice and Bob who want to instantiate the information processing task. On the other hand, there's James who wishes to disrupt it. So what are the relative strengths? What are the relative weaknesses? What are opportunities? What are threats, right? If you ever went to business school or attended one of those talks, this sort of analysis is all the rage, and that's, in some sense, that's what we'll be doing in this talk. Like beyond the specific examples I'll be talking about, I'll try to abstract away to the extent possible general principles that abstract away to other problems as well. All right, so of course, the way I presented it, it's a very general setting, and I don't claim that really we can solve all the problems simultaneously. So really the flavor of this talk will be, I'll be talking about specific scenarios, outlining what's known in them, and then talking through them. So in that spirit, let's start off with, a concrete task, that of reliable data storage. So let's say that, there's some number of computers, let's say C computers in a server system, and a client wants to store some large file by storing it across these C servers. So maybe the file is very large, you can't store it on a single server. Besides, you want to add some redundancy for reliability, right? So you want to distribute it across that. And just to be concrete, just to have a concrete example at hand, like let's say that the message, the file you break up into 3 pieces, M1, M2, M3, and then you store in, let's say, 5 servers. Oops, I'm sorry, some of the animation must have persisted, I apologize. So you break it up into 3 pieces, and then, you code it somehow, you add some redundancy. So the first 3 pieces you store on 3 servers. So just for concreteness sake, let's imagine that the file is 3 gigabytes. So each of these servers can store a gigabyte. And so you store 3 gigabytes on these first 3 servers. And then for whatever reason, you add certain linear combinations. These are linear combinations over a finite field, if it matters. It doesn't really, but basically you're adding some redundancy, storing it in other servers. And why are you doing that? Well, because, if something goes wrong, like let's say one of the server crashes, another one starts spitting out garbage, then you can still hope to recover from something like this, right? And it turns out that if these are random failures, so like a random computer failure, or a random garbage output from a computer, those can be modeled by, you know what, let me just see what's going on with the animations and switch it off. These slide transitions are a little bit, it may have been, it may have been the rehearse timings thing, which is just changing these slides. I apologize. Well, okay, I'll try to keep an eye on what's going on there. It was not happening earlier, but you know how it is. Okay, so anyway, you've split up the file into 5 pieces. You've added some redundancy, stored it on these 5 servers, and if there's random noise like an erasure, a computer just vanishes, the server just vanishes, or it spits out garbage. In both of these cases, you can, well, if it vanishes, you know it's vanished. If it's spitting out garbage, you can detect that quite easily just by, you could imagine putting some checksums in it, and therefore you can ignore it. And then once you have what is definitely true, M2, M3, and the sum over here, then as you can imagine, you can solve a system of equations and retrieve M1 as well from something like this. And you can convince yourself that regardless of which combination of 2 out of 5 servers goes off, you can retrieve the 3 pieces of the file from the remaining 3, right? So this is always doable. This is, for those of you who know about these sorts of things, this is like an error correcting code. It's in particular a Reed-Solomon code. So we have good ways of dealing with this. And basically to abstract it away, to put it in the in the language of an information processing system. So if you have 3 pieces of information, you've added some redundancy, made into 5 pieces of information, some random noise happened. And then from these observed pieces of information, once you throw away what is obviously incorrect or what is not available, you can retrieve the data from it, right? And in the language of Shannon, so if there are C servers, Z failures, so this is, we basically kind of can show the capacity. So we've shown that as Z, the number of failures increase, then the capacity, the number of pieces of information, roughly intuitively, that you can store decreases, but it decreases in a sensible manner as C minus Z, right? If a certain number of servers vanish or are not reliable, then you can't really hope to store information in them, even if you knew in advance which ones they were, and even if you didn't know which ones they were in advance, nonetheless, that sort of a coding scenario can still let you store information at this rate. So we know you can't hope to do better than this, and indeed you can do this much, right? So this is the capacity theorem. It's a capacity theorem. So this is a benchmark. Now, this sort of a thing is, of course, not new, but it's just a benchmark for us to understand what is possible, what's not. So let's look at something slightly more novel, more interesting. So, okay, well, let's look at something that's also classically known, but in this adversarial setting. So if a hacker can corrupt a certain number of servers, let's say ZW servers, then in fact it's known that you pay a severe penalty, that instead of C minus Z or C minus ZW, you can't hope for anything more than C minus 2ZW because of something called the Singleton Bound that I'll describe in a little bit. And indeed, you can achieve it via slightly more sophisticated sort of decoding strategies for read-Solomon codes. So you can achieve that performance. So where does this penalty really come from? So informally, what does the Singleton bound say? It's a fundamentally combinatorial bound. It's not even that hard to prove, but in the spirit of not necessarily diving into math, which isn't necessarily directly relevant, I won't necessarily go into it. But informally, what it says is, if you store R pieces of information on C servers, so think of each of these R's being like a gigabyte being stored on a server which can store a gigabyte, for instance, then there have to be at least 2 distinct messages whose corresponding encodings, like whose corresponding stored bits, match on C minus R of these servers, right? Which kind of, well, I don't know if this makes some sense. I mean, if you can kind of imagine it perhaps by something like a generalization of a pigeonhole principle, which is really how this bound is proven. Because if you have if R is kind of large, then if you discard C minus R of those servers, then the C minus R of those pieces, then the remaining pieces, like they'll have to be some overlap between them, right? So that's kind of how you prove the Singleton bound. But anyway, so that's what the Singleton bound tells us. And with this in hand, well, then what can James the Jammer do? He can say, well, okay, so if this is maybe some X that was actually stored on these servers, I can figure out, well, what is the nearest X prime? What is the most confusable X prime for this? What is the most confusable sequence for the sequence that is actually stored on the servers? And then I will carefully corrupt the servers in a manner such that I end up with something right in the middle, right between the 2 things that could have been stored, right? So if the 2 things that could have been stored were, for example, 54103 or 34205, so in this case, they differ in, they're the same in 2 locations, they differ in 3 locations, right? So if the adversary can corrupt 2, for instance, if he can corrupt 2 of these, so he knows that they differ in these locations, the 5 and the 3, the 1 and the 2, the 3 and the 5. If he corrupts 2 of these, he can make whatever is received look more similar to something else rather than what is transmitted, right? So note that a random noise would be unlikely to work in that manner, right? Random noise would be unlikely to corrupt the 5 specifically to a 3, the 1 specifically to a 2. But since it's an adversary, he knows what is being transmitted and he knows what he wants to corrupt it with. So in this manner, because it's a sentient adversary, so to speak, he can carefully, deliberately add some noise to deceive the receiver, right? And this would the data constructor, and this is what causes the issue. All right, so so with this in mind, then it perhaps behooves us to think about, well, what can we hope to do to ensure that, well, so we care about storing data on these server systems. What can we do? Like, is this really the best we can hope for? And one is allowed to perturb models in reasonable manners. So maybe we make the reasonable assumption, perhaps, that some adversary, a hacker, may not be able to corrupt. So maybe he can't see everything. So implicitly, if you think about what happened over here, we implicitly assumed that the adversary, the jammer, James, was able to see precisely what was stored on each of the servers, and thereby determine his attack strategy, right? So even if he can corrupt only 2 servers or something, he still nonetheless needs to see everything on all of those server systems before he can decide how to optimally design his corruption pattern, right? He should not corrupt servers which are already identical so as to save his energy, and he should change the others in a manner such that it would cause maximal confusion, right? But perhaps that's too strong a model for the adversary. Maybe the adversary, again, this is okay. Let me just spend a minute or two seeing if I can figure out report slash setup show. Is this where the timings are? Oh, manually. Okay, good. All right. Hopefully that solves the auto change, the auto slide transition problems. Okay. So maybe, as I was saying, maybe the assumption that the adversary already knows what is stored on all the servers in advance is too strong an assumption. Maybe he can hack a certain number of servers, but hacking may mean different things for different servers depending on the sort of security on each of these servers. So maybe there are a certain fraction, like which I'm calling ZRO for read only. So a certain read only fraction which he can only read, a certain write only fraction which he can overwrite without knowing what was originally on them, and a certain read write fraction which he can do both on, right? So these 3 numbers parameterize the adversary's power, and we allow them to be anything as long as they're less than the number of servers, of course, there's some, and then we can see, we see what we can say. So so in this case, so I apologize for the slight change in what the adversary looks like. This is now Calvin. So Calvin is the adversary. I'm stealing slides from a previous talk, so it was a bit too much to change all the adversaries everywhere, but anyway. So Calvin is going to be trying to disrupt communication. So here's the sort of result that we can prove in this case. So in some cases, when the adversary is in a so-called weak regime, then the optimal rate we can hope for is actually quite optimistic. So if you think about it, ZRW is the number of servers where the adversary has read-write privileges, and ZWO is the number of servers where he has write-only privileges. So read-write plus write-only, that's the number of, so together, these 2 numbers together are the sum of the number of servers he can corrupt, right? And therefore, but we anyway know that if the number of, you can't hope for C minus the number of corrupted servers. You can't hope for any better performance than that. A certain number of servers have been corrupted, can't store anything in them, right? So in some sense, if the adversary is in a so-called weak regime, then you can hope for this throughput, this performance, which is as if the noise was random, as if his corruption was random. On the other hand, there's going to be a different regime, a so-called strong adversary regime, where the best rate we can hope for will be substantially less, right? And really what we can show is, so the type of results are, so remember again, these 3 numbers can be at most C, right? The overall number of servers that the adversary can attack is at most C. And in a certain fraction of them, like as long as a certain equation is satisfied, so as long as you're in some tetrahedron over here, I'll explain why these parameters come about, but right now let me just try to describe what the result is, not why the result is. So the what of the result is that if these parameters satisfy some constraints, then the adversary is so-called weak if they're inside this tetrahedron. On the other hand, if they're outside this tetrahedron, then it'll be a strong adversary. Okay, so if it's in the slightly shaded region, then it'll be a strong adversary. And so again, just to repeat once again, so in a certain parameter regime, you can make the adversary just behave like random errors or crashes, and in a certain other parameter regime, the adversary can be more mindful, and in particular, he can try to deceive you in a more careful, mindful manner. Yeah. So so let's view this as a communication problem, because really what's happening is the person who's initially storing Alice, who's initially storing the things or the data on the servers, is putting something on them, then goes away. Then Calvin comes along and he starts like jamming. So in this case, so these symbols here. So this ear means he can hear or see what's on this thing, and he can also jam what's on this thing. So he can basically cause disruption on X2 over here. Yeah. And then he changes it somehow, and then Bob. So this Bob over here, I don't know if anyone recognizes this Bob. This is Bob Michaelis, a famous coding theorist. I was fortunate enough to be taught by him. So if anyone can possibly hope to decode a message, certainly Bob, a Shannon theorist, could, right? Shannon Award winner. So therefore, it's Bob's task to retrieve this information. So in this case, here's from an achievability perspective, from the perspective of trying to get good performance. Here's an idea which is quite helpful, that of so-called pairwise hashing. So the idea is, imagine you take your Alice takes her message. Again, add some redundancy, stores it on different servers, just like we did earlier. M1, M2, M3 stored as M1 plus M2, M2 plus M3, different combinations of that message, right? But then over and above that, she adds some very short random keys, and she stores pairwise hashes. So what are these pairwise hashes? So with respect to every payload packet and every key within that packet, within that server, there's going to be a hash of that other payload. So think of it as the information stored on this first server over here contains within it a hash of a signature of the payload of each of the other servers as well. Okay, so it's as if each server is storing signatures of what the other data should look like, but it's storing these signatures using random keys that are known only to that specific server itself, right? So and let me just drill down on this, because it's I mean, maybe the idea itself isn't complex, but it's at an abstract level it'll be important. So the idea is that this encoding, this way of adding redundancy, this way of taking this message and then adding redundancy to it, has implicitly within it extra randomness, extra stochasticity, which the adversary may not have direct access to. Because remember, in this example we are looking at, Calvin or James or the jammer basically only has access to this middle link over here, right? So therefore, he doesn't necessarily know the keys on these other links, on the first link and the third link, right? And therefore, his jamming scheme, which is not aware of these secret keys, may not be optimally designed to be able to cause damage on these other links, right? And that's what we'll implicitly leverage over here. So how is this useful? Well, oh yeah, just a quick remark over here. So these payload things, think of these payload things as large pieces of information, and then we are storing just small keys, small hashes. So this is just like a small header to the information that we're storing on each of these servers. Yeah. And there's some details here, which I'll just sort of skip over. There's certain types of hashing schemes which are better than others in this case. But basically, if no corruption happens, then everything is fine. You know, all the hashes are pairwise consistent. So Bob, on observing something like this, can say, okay, let me look at, for example, H12. So I'll take a hash of X2 with K12 and see that it does indeed match H12. So if nothing has been corrupted, well, the hashes are still pairwise consistent, right? On the other hand, if Calvin or James had jammed the second link, then in this case, the adversary James could have changed this in any manner he wished. He could have changed these keys to be anything else, these hashes to be anything else. But the point is that the point is that the hash on, for example, the third link would not match with the payload if the payload here has been changed, right? If X2 has been changed, because remember, critically, this hash depends only on the K32 and Y2. And since K32 is not known to the adversary, therefore, any non-trivial changes he instantiates in X2 to make it Y2 will, with high probability, be detected. Now, at this point, the decoder doesn't know whether to trust the second packet or the third packet. All he knows is that there's an inconsistency between packet 2 and packet 3. That's all that he knows, right? But what he can do from this point onwards is to build a consistency graph. So the decoder Bob can say, okay, so packets 1, 2, 3, 4, and this thing is 1, 2, 3, 4, 9 are consistent. Maybe 8, 7, 5, 6 are consistent, but there's no pairwise consistencies between these. So maybe packet 1 and packet 8, their hashes do not cross verify, right? So what does he do? The decoder just picks the largest click, picks the largest set of self-consistent nodes and uses that to decode. Okay. Generally speaking, for finding the largest click is an NP hard problem, but for this particular problem, you can show that it's easy because for the correct click, it basically just comes down to counting the node degree. There's some details here which I won't dive into, but basically it's computationally easy. So why does this work? Oh, there's a typo here. This is a different type of jamming. Ignore this phrase over here. So why does this work? So if you think about it, well, what can the jammer do? So the jammer can, of course, corrupt anything he wants on the read-write links, on the write-only links, and he can make it consistent with whatever he's observing on the read-only links, right? So if there are these 4 types of nodes, there are the read-write links, read-write servers, read-only servers, write-only servers, and some untouched servers, right? So of these 4 types of servers, 3 of them can be made self-consistent, right? On the other hand, the encoder's true click, like the uncorrupted data, corresponds to the information on the untouched links and on the read-only links, right? And the sum of the untouched links and the read-only links is precisely, the overall number of servers. Sometimes I call them links, sometimes I call them servers. I apologize for the phraseology because this setting is useful in a variety of communication settings as well. So anyway, the set of uncorrupted servers equals this much in number, equals the overall number of servers minus the number of those where the adversary could have corrupted, could have overwritten something on those servers, right? So this scheme over here, and remember what the scheme is. The scheme basically comes down to the decoder finding the largest click and then using that to decode. This will work as long as the decoder's click, as long as the largest click corresponds to uncorrupted servers. That's what is needed over here. So what that comes down to is requiring that this number over here be larger than this number over here, right? And that's precisely what we had in our condition. So as long as this equation is satisfied, and you can bring these 2 numbers over here, and then you get the weak adversary regime. So if it's a weak adversary regime, what can you do? You can basically figure out whichever servers the adversary has actively corrupted the payload of, discard them, and then use the remaining servers to figure out what is going on. Yeah. So okay, so that's the achievability over here, and to show that you can't hope to do any better. So to show that you can't hope to do any better, like for example, if there are 5 servers, the adversary can read one, has read-only privileges in one, write-only on 2, read-write on none. Then the best rate you can hope for, the best amount of information you can hope for is at most 1. Like that's an example of something like this. So if you want to prove something like this, how do we do it? Well, it's via the so-called stochastic symmetrization. So again, the way to think about this is it's basically like that same deception strategy, but done a little bit more mindfully over here. So what does the adversary do? So he has, so Alice has a message. As a function of this message, she stores 5 pieces of information on 5 servers in any manner whatsoever. Doesn't have to be like that previous scheme I described. So this attack strategy that I'm describing will work regardless of how Alice does this, right? Now, what does Calvin do? So he picks some other fake message, which is consistent with what he observes on the one link that he can observe. So remember, he can read only one server, right? So he picks some M prime, which is consistent with what he observes. And you can show that if you try to store more than one piece of information, if overall there is more than one piece of one bit of information somehow in the system, then there must be some M prime, which is different from M, which also matches on the one link on the one server that the adversary sees. Okay, let me repeat that. So here I'm trying to argue that if you're trying to store too much information, so if you're trying to store more than one piece of information, then there will be some M prime different from M, such that both M and M prime have precisely the same information stored on that first server, and they may differ elsewhere. Okay, and this is again really just a consequence of the Singleton bound. Okay. So given this, now even though the adversary Calvin over here can only read this one server, so he only sees this, he has write privileges on 2. So what does he do? He tosses a coin and decides to either corrupt the 2nd and the 3rd server or the 4th and the 5th server, and therefore replace x2 x3 with x2 prime x3 prime, or replace x4 x5 with x4 prime x5 prime, right? And now the point is, Bob, so Bob will, in the first scenario, either observe this, or in the second scenario, observe this. Yeah. And the point is, on observing either of these, so for example, suppose Bob is observing x1, x2, x3, and then x4 prime, x5 prime. Bob cannot distinguish between the scenario that Alice had this message and had these 3 pieces of information, like x1, x2, x3, and then Calvin replaced x4, x5 prime, or that Alice indeed had M prime. So in particular, she had x1, x4 prime, x5 prime, and Calvin replaced x2 prime, x3 prime with x2, x3, right? So it's a symmetric situation, and that's why this sort of an attack is called symmetrization, right? And at its core, many of these different types of jamming strategies, it's a relatively straightforward strategy to conceive of, to implement, but at its core, it actually turns out in many different scenarios, whenever we know what the optimal performance is, it comes down to something like this. Now, to show that, well, we have to match it to the corresponding achievability scheme, which we just did, right? So in these previous slides, I showed you some click-based scheme that showed that you could always get a certain performance if you were in a certain regime. And over here, I'm showing you how you can't hope to do any better than this in this parameter regime, right? So yeah, so in this case, Bob would be confused, and you wouldn't be able to infer what is a true transmission. So there's some details here which I won't go into, some technical details, like you have to make this robust to private randomness used by Alice and so on. It turns out that using relatively standard tools in information theory, you can make it robust to that as well. So it requires some fusion between the tools of information theory and those of coding theory, which are more combinatorial nature. But at this point, we sort of know what to do over here. Yeah. All right. So I have around 10 minutes left, and of course, way too many slides. So, I'll do what I can while trying to make sure that that people can walk away with something. So, some takeaways are these. So the jammers, deception, symmetrization attacks can do more damage than just random noise attacks. And stochasticity, like as long as there's something that's hidden from the adversary that he or she doesn't know, then this can help combat jamming strategies. And it's the tension between these two that in some scenarios, like for example, in these sorts of problems, I only talked about one specific scenario. There are many different scenarios you can analyze, and we can basically figure out the capacity in each of these, right? Optimal storage strategies in all of these. All right, so so moving on, let me talk a little bit about some jamming resilient communication schemes. Well, let's see what's the, okay, fine. So let's talk a little bit about jamming resilient communication schemes and see if there's some other messages to take away. So in this case now, Alice has some message, she encodes it. She encodes it into some vector. So imagine like Alice has a radio, she's transmitting some vector over Rn to Bob, but she has some power constraint. So she can at most transmit vectors with a certain L2 norm. In this case, this square root of NP captures somehow a power constraint, how much energy she has at her disposal. And then the jammer himself has some power constraint, some square root of Nn, right? And then this is these two signals, these two vectors literally just get added over the air, and then based on what you receive, you have to figure out what was transmitted. So this is a scenario that we'll talk about now. And again, it's good to have a baseline comparison. So Shannon tells us what the capacity is if this noise is random. For instance, if it's Gaussian, additive white Gaussian noise. So this is the well-known and analyzed AWGN channel. And the capacity, the best throughput, the maximum amount of information you can transmit per channel use is well known. So the way to think about this is that as the signal to noise ratio increases, as long as the transmit power divided by the noise power increases, then the best rate, the best throughput you can hope for also increases via some function like this. Yeah. And at its core, it's a fairly nice geometric argument. It basically says, if you choose like random noise balls of radius square root of Nn, like basically like if you transmit some X, then the noise ball around that transmitted X will look sort of like this. And Shannon theory at its core is something is mostly, not always, but in many scenarios, it comes down to soft packings of these balls in high dimensions. So it says that you can have lots of these balls which have small overlap between them, and as long as you don't get too greedy, you don't try to transmit more than at this rate over here, then you can get you can reliably figure it out. If you try to transmit at too high a rate, then you'll get in trouble. So now you can think about adversarial jamming strategies, and just like we alluded to earlier, this is also much trickier. So there, since it's an adversary, so then you have to think about, well, hard packings rather than soft packings, because now if there's any overlap whatsoever, for example, if there's some overlap between X3 and X2 over here, well, then the adversary would choose noise to fall in the middle, right? Random noise is much more benign. It won't necessarily go in that direction. Indeed, with high probability, it doesn't. But adversarial noise would deliberately seek out the nearest code word to try to corrupt it, right? So, and these hard packing problems are much trickier. Generally speaking, the capacities are not known. Inner and outer bounds of the performance are known. Some complicated functions via fairly sophisticated combinatorial arguments, but I'm not going to go there. Yeah. But it turns out, in some weakenings of these adversaries, you can give some capacity theorems. And so, for example, if you have a so-called oblivious adversary, so the jammer is indeed trying to jam communications. He knows the communications scheme, but maybe he's half duplex. So, as an engineer, what does half duplex mean? It means you just have a single antenna. You can either transmit or you can receive. So if you're trying to figure out what is being transmitted, then you can't jam, right? So if you're jamming, then you don't know what is being transmitted. So that's why this is a so-called oblivious adversary. I mean, it's a crude approximation to a relatively simple sort of jammer, but it's an attempt to begin to try to state theorems about situations we can analyze, and there are more situations I can say something about. But basically, an oblivious adversary is something like a blind adversary. He has to try to jam without knowing what is being transmitted. And in these cases, you can sort of get to the Shannon capacity up to a certain point, as long as the transmit power is bigger than the noise power. Otherwise, it's zero. And in this case, in this very specific case, it turns out, well, the symmetrization strategy, the jamming strategy, is actually sort of the obvious one. In this case, the jamming strategy is, well, if n is bigger than p, if the jamming power is at least as large as the transmit power, then the symmetrization strategy simply comes down to the adversary choosing noise which corresponds to a potential different transmitted code word, right? So if that is the case, then what would Bob receive? Bob would receive the truly transmitted code word plus some other code word, and therefore, on being given the sum, would not be able to figure out what was transmitted, right? So in this case, again, it's a symmetrization strategy. Bob can't distinguish between these two, and therefore that gives a converse. The achievability requires, so arguing that even in the presence of an adversary, when p is bigger than n, you can indeed achieve the same performance as in an AWGN setting, actually requires some nice ideas. So to speak to that, let me actually jump ahead and mention a couple of other things that help in these adversarial settings. So it turns out, if the transmitter and the receiver share a small number of bits of common randomness, then you can essentially reduce it to basically a problem where even if it's an adversary, it behaves like random noise at a very high level. And why does that work? So it turns out, so again, you can get to this capacity, which is just the capacity of an AWGN channel. And this is even if there's an adversary, there's a jammer who is not blind, who can see precisely what is being transmitted, but the one thing that he doesn't know is some common randomness that is shared between the transmitter and the receiver. Yeah. So the thing that's really useful over here is this tool called list decoding. So what list decoding gives us is it's a fairly remarkable phenomenon. It says that even when you have adversarial noise, and even if the adversary can always try to do something where he tries to confuse you between one code word and another one, you can still prove that he can never confuse you between too many code words. He can still never try to confuse you between more than a constant number of code words from the random code. So there's some epsilon delta happening over here, but basically, if you try to get up to epsilon close to the Shannon capacity, the adversary cannot confuse you with more than 1 over epsilon code words, roughly speaking. So and this is a very useful tool to have in your toolbox, because it says, okay, you may not, like in an adversarial setting, the decoder, the receiver may not be able to exactly infer what was being transmitted by the legitimate transmitter, but the adversary will never be able to confuse you by between more than a constant number of alternatives. So if this is the case, then you can use, so for example, if you have additional common randomness between the transmitter and the receiver, you can use that to disambiguate between the small number of alternatives. So list decoding is often therefore a very useful first step in proving any sort of achievability result over here. Yeah. All right, so being cognizant of time, I'll sort of skip over some of the other results known, which deal with somewhat more sophisticated scenarios, which deal with many of the other things all folded into a single thing, lots of pretty pictures, just ignore this. But let's try to abstract away the, so maybe at a high level, let's try to end with an abstraction of the sort of deception strategies that we talked about. And this also can be generalized in very general settings. So you have a message, you have an encoder. So in general, you can transmit some code word or some arbitrary alphabet. There's an arbitrary channel law, which combines the actually transmitted code word and the actually jammed sequence to some other output sequence. So, I mean, take my word for it, this is a very general setting. This can capture a whole bunch of different communication scenarios. So in this case, it turns out you can write a very simple set of linear equations which capture a so-called symmetrization scenario, which basically at its heart corresponds to the following thing. So the transmitter transmits some true sequence. The jammer chooses some other random sequence from the thing, and then symbol-wise, just symbol-wise creates his jamming sequence as a function of this sequence over here, and this is what actually happens. This is what gave us the Y. But it could have been the case. You could imagine a contrapositive experiment where the transmitter was instead transmitting X prime, and the jammer had chosen X. And then you could have resulted in the same pi. So it turns out, like, even though these quantities over here are vectors, you can convert them into single layer expressions. That at its heart is what is the magic of information theory. Even though information theory deals with long sequences of variables, you can make statements with single random variables, and they tell you something about those long sequences of random variables. So at its heart, the same thing is happening here with these symmetrization equations. So if this is the scenario that you have in the true long sequences of transmissions setting, if you look at the corresponding symbol-wise equations, and if these two equations can be made to be equal to each other, then you can symmetrize. So at its heart, basically, there's some sort of a symbol-wise jamming strategy where the adversary picks a random code word, symbol-wise adds some, does something to it by passing it through a conditional probability distribution, and that's how he'll choose his jamming distribution. And if something like this happens, then he can spoof. And if and that's actually the easier part of the proof. The harder part of the proof is to show that if this equation doesn't hold, then there are clever decoding strategies which leverage the fact that the symbol-wise thing cannot be made to be equal. So these two scenarios, X and X prime, cannot be made to be equal. So because these symbol-wise equations don't hold, so then when you look at the vector-wise transmissions, when you look at the full sequences that the transmitter truly transmitted, that the jammer tried to use, then there's going to be some statistical difference that you can leverage to distinguish between the truly transmitted sequence and the fake sequence. Yeah, and this statement is true regardless of the jamming strategy that the adversary used. So at its core, it comes down to first using that black box of less decoding, coming up with a small set of alternatives, then checking between all pairs of alternatives, running some sort of a tournament, and like some complex analysis. This is some beautiful work by Cesare and Narayanan in the 80s, and we're still working through the consequences in a whole variety of different settings. So I'll leave it at that, except just this turtle pic video, which is kind of cute. So you may have seen things like this, right? You can feed things to a machine learning algorithm, and you can perturb it just slightly, and then it thinks, oh, this is a rifle or something like that, right? And at its core, it's sort of the same phenomenon happening over here. You have some source of information. You have some source of information. An adversary is carefully selecting how to add noise to it to perturb your encoder over here. In this case, your estimator over here, to cause an error. So for simplified versions of this, I don't claim to have a theorem for precisely this estimation problem, but for simplified versions of this, we have some capacity theorems. This is too much to digest right now, of course, but again, similar ideas, adding some noise carefully and so on can help a lot. Okay. All right. So I'm over time. I'll leave it at that. I'm happy to take questions.
Brilliant. Thanks very much. That was really clear. You're not over time because we started late. So yes. Does anyone have questions? Okay, well, I'll kick off whilst you're thinking. In halfway through the talk, you introduced Ollie has a question. Ollie, you go first.
Sure. Okay, thank you. So yeah, lovely talks, and thank you. I guess there's a lot of bounds where there's an upper bound and a lower bound on the true performance. Do you have any kind of instinct or hunch as to which the right bound is? I mean, you know, if I were to get into this area, which direction should I try to go to try and prove these things, do you think?
Yeah, so even the canonical problems where like if you just want to do hard, so let's just look at this thing over here. Yeah, so this is a remarkably simple to state problem, right? You have a sphere of a certain radius, and you have spheres of smaller radius, all in 9 dimensions here, and you want to pack as many as possible of them, right? And this problem has, of course, been open for a long time. The achievability, the best packings known, are remarkably simple. So they're basically just greedy packings. They just come down to saying, choose one arbitrarily, throw away the forbidden region for this, then choose another one, and so on. And it's basically just that sort of greedy packing, which gives us the best thing known. It's not even that hard to write down. And people have, since the 50s or 60s, been trying to beat this, but nothing is known. People suspect, I mean, okay, there are different camps, but probably the majority of people suspect that this simple strategy is indeed optimal, mostly because, you know, lots of smart people have tried, banged their heads, and they haven't been able to improve on that. I'm one of the few who actually doesn't believe this. I've been recently trying, you know, of course it's a fool's errand, but one can only hope, right? So I'm trying some non-trivial strategies. I'm happy to talk about them if you're at all interested. But yeah, the converses require sophisticated linear programming combined with duality, combined with like a whole bunch of other tools, which also have not been improved since the 70s. So, you know, I mean, these are hard problems, really. So it's only at the margins where you start perturbing the model even more that recently, over the last 10, 15 years, we made some progress. But for this clean problem, like I think, well, maybe there's some progress to be made. And again, I'm happy to talk about it with you offline. But other than that, yeah, it's been open for a while.
Cool, thank you.
Yeah. So my question was about the hashing that you introduced.
Yeah.
And so specifically, so I thought that one of the main vulnerabilities that this system that you were describing had was the linearity in the coding at the beginning, right? So my understanding was that if you could hash everything, then the adversary would be significantly less powerful in this framework. So I was just hoping for a little bit of clarity on what the hashing is done. I mean, is this cryptographic hashing that the adversary can't hack?
No, yeah. So I should have said upfront, everything in this talk is assumed to be information theoretic. There's no computational assumptions being made over here. So the idea is really like, so imagine there's some payload over here, and then it's kind of like so what I'm going to describe is not going to work for some reason, but imagine like so there are certain pages of a book over here, right? So page number 1 of a book, page number 2 of a book, page number 3 of a book, and now these keys over here say okay, the 39, 45, 63. And then what's stored over here is the 39th word of the second page, the 43rd word of the third page, and so on. And the point is, now if the adversary changes the contents of the pages, then it'll be clear, aha, So this hash doesn't match what is stored over here, and perhaps vice versa, right? If he changes these hashes as well. So the point is, it's just that it flags a pair of which you must be suspicious of one. So at this point, you don't know which one, but you know that at least one of these two is suspect, right?
Yeah.
And from that point onwards, then it becomes a numbers game. So then you know, okay, all of these are consistent with each other. So either they're all trustworthy or they're all trustworthy. But at its heart, we have an honest majority. Like that's what that parameter regime tells us. So that's why it works.
Mm-hmm. Thank you. Yeah. Are there any other questions? Okay, well, the 3 o'clock bell has just tolled. So I'll just thank you once again. That was a really excellent talk. And
Thanks.
I'm very clear. So thank you very much.
Thank you again. Take care.